You're about to learn an awesome trick to solve the derivative that you're going to see below. So if you want to ace your calculus exam, smash that like button and subscribe like a ninja. Let's say we want to take the derivative of x to the x. And your first approach might be, you know what, I've seen polynomials before. So for the case of a polynomial, I'll take the power of x, bring it in front, multiplied by x raised to a power that's 1 less than it used to be. And this approach looks like it works, but believe it or not, it gets you the wrong answer. Can you tell me the mistake in the comments below? Okay, so remember for polynomial derivatives, this only works if the power of x is raised to a power that's a constant, such as 3 or 2. So your next approach then might be to say, you know what, this looks like a good case of using the chain rule. And you're getting warmer, so you're going to want to stick around because we'll show why the chain rule is in fact the approach. And I'll show you below, but before we get to it, you got to be careful here as well, because if for this problem, you just go ahead and use the chain rule with it being written as is, you're going to run into another trap. See, for your outer function x to the x, when you want to take the derivative of that times the derivative of the inner function, which would be, say, the power of x in this case, what on earth is going to be the derivative of your outer function x to the x? Now it's basically like a chicken and egg problem, because you are now trying to take a derivative of the outer function, which is the whole point of this question. So this is where we get to use a really cool hack. We're going to manipulate this original problem to look a little bit different, so the chain rule is going to be much easier to work with. So what I want you to remember, whenever you see a problem like this, where you've got powers such as x to the x, etc., remember that this might be hinting that you could use a cool application of natural logs and exponents. Remember for x, I can actually rewrite x as e to the natural log of x, because if you remember on the left-hand side, e to the natural log of something basically cancels out. And the reason why this is a really nifty trick is we can then take the original problem x to the x and rewrite it in such a way where now we have e raised to the natural log of x to the x. You might be wondering, okay, why are we doing this? Aren't we making the problem look like it's a lot more complex? Well, yes and no. It looks kind of weird, right? But if you bear with me, you're going to see just below why we're doing this and why specifically with the chain rule, it gives us the ability to use some magic right here. The way we're going to proceed is we got to first remember what the chain rule is. The chain rule talks about a composition of functions, f and g. So for instance, in this case, for x to the x, when we rewrite it as e to the natural log of x to the x, f can be treated as the outer function here, which is e raised to some power, while g, that composite function, can be basically the power itself, which is natural log of x to the x. And so with the chain rule, what this allows us to do is for that inner function g, in other words, the power we're raising the function to, if we call it this variable u, then the original problem we're trying to solve, the derivative of x to the x, can be rewritten as the derivative with respect to u of this outer function f, where we've substituted in u, times the derivative of the inner function with respect to x. So in other words, to make that a little bit more clear, if we're rewriting x to the x as e to the natural log of x to the x, then our outer function would be e to the u, where u is simply the power of natural log of x to the x. And then we can then take that derivative in terms of u times the derivative of that inner function, which was natural log of x to the x. And so it's kind of like unpeeling the layers of an onion if you think about it. You've got this outer layer, which is f, and the inner layer, which is g. And so when you write the terms out for the chain rule here, what this means then is that when we plug in what u is into the function e to the natural log of x to the x, then our derivative simply becomes a derivative with respect to u of e to u, because we've plugged in what g of x is for u, times the derivative of the inner function with respect to x. And remember, u is simply g of x, which is the original power, natural log of x to the x. The cool thing now is that we're going to really see how the chain rule here pays off, because the derivative of e to the u is simply e to the u itself, which is really nice to work with. But then now we multiply it by the derivative with respect to x of natural log of x to the x. And this is where we get to use a really cool property. Remember now with logarithms, when you have the natural log of x raised to a power, you can bring that power out in front of the natural log function. So then when we take the derivative of x natural log of x, we can then use the product rule here. So this becomes e to the u times, in parentheses, the derivative of the left side of that product, which is the derivative of x, which is simplifying to 1, times natural log of x, plus the derivative of the right-hand side, which is taking the derivative of natural log of x, giving you 1 over x, times the left, which is x. And this simplifies further to e to the u times in parentheses the natural log of x plus 1. And when we distribute e to the u through every term, this results in e to the u natural log of x plus e to the u. And we're done, right? Well, wait, not so fast. We have a problem now. We have something written in terms of both x and u, but the original problem had just one variable x. So we can't just stop here. We need to remember to plug back in what u is, which is natural log of x to the x. And so when we do that, we get e to the natural log of x to the x, natural log of x, plus e to the natural log of x to the x. And this is where you can then finally simplify the expression for e to the natural log of something, because now we're getting our final answer, right? And this is the beauty of the mathematics here, is that sometimes you don't want to simplify an expression until it's necessary. And this is where we want to do it because it gets us the final answer.